Okay. So, we continue with that exercise. We are carrying on a convolution at n equal to 0 first. So, we are multiplying n is 0. So, h r into g r. For all r, we have to multiply and then sum. So, this is h r sequence, this is g r sequence. G r is nothing but x minus r. Okay. This was the definition. G r is x minus r. Okay. So, it gets x, the sequence gets flipped, that is from positive side it goes to negative side, it is called flipping. G r is nothing but flipped version of x r. X r was here, 0th sample remains as it is, but first sample goes to minus first, second sample goes to minus second. So, right hand side goes to left hand side. If there are left hand side samples, they would have gone to right hand side also, because it is minus. So, g minus 1 means x plus 1, g minus 2 means x plus 2. Okay, from right hand side they go here, g minus 1 minus 2. G plus 1 means x minus 1. So, x minus 1 from here would have gone to the right hand side. Okay. G plus 2 means x minus 2. From here it would have gone to 2. Their values are 0. So, that is why zeros are going. And we have to now carry out the convolution for various values of n to understand the matter. So, I am starting with n equal to 0. So, if n equal to 0 means just g r, x r g r for all the r's and add. So, if I just multiply for various r equal to 0, this into this, r equal to minus 1, this into this, but r equal to 1, 0 into something, r equal to 2, 0 into something. So, they do not contribute. R equal to minus 2, so this into 0, r equal to minus 3, 0 into 0, r equal to minus 4, 0 into 0, they do not contribute anything. You are left with only these two terms, 4 into 1 plus 2 into 2, 4, so 8. So, output is 8. Okay, output convolution output, if you call it y n equal to 0, 1, I mean 8. Then consider n equal to 1. N equal to 1 means is r minus 1. So, g r is to be shifted to the right by 1. Then I have to carry out the product. So, that means if you take this g r, if you shift to the right by 1, 4 will go to the 1, 2 will go to here. Okay. So, it will be like this. Which is equivalent to x of 1 minus r, 1 is n. So, this will be g r shifted by 1. So, 4 will go to 1, here the value will be 4 at point number 1, then 2 will go to 0, 2, and 1 will go from minus 2 to minus 1, and then zeros. Okay. Now, if you do sample wise multiplication, 4 into 2, 2 into 1, 1 into 2, and then 0 into 0, 0 into 0, they do not contribute anything. All right. So, 8 plus 2, 10 plus 2, 12. So, next value is 12. Sorry, next value is 12. In the same manner, for n equal to 2, n equal to 2, how much will be n equal to 2? This is shifted to the right by 2. So, minus 2 will come below this, this point will come below this, that will give rise to 1 into 1. This 2 will come below this, that will give rise to 2 into 2. So, 2 into 2, 4, and 1 into 1, 1. 4 will come here, but that has 0, that has 0, and so no contribution. So, only minus 1 will come with this, because shifted by 2. So, minus 1 will come here, sorry, 1 will come here from point number minus 2 to point number 0, 1 will come, jump by 2, it will find 1. Then 2 will move to here, it will find 2. So, 2 into 2, 4, 1 into 1, 1. this 4 will move here, but it finds 0. So, nothing. So, 4, 2 into 2, 4, okay, and 1 into 1. It is like this. This is getting shifted further, already shifted once, it is now getting shifted further by 1. So, this comes here, this 2 goes here, this 4 goes here. So, if you align with this with this with this, that is all. Okay. So, we will have 1 plus 4, 5. Then n equal to 2, it will further shifted. Okay. It will further shifted. So, you will have 1 going here, 2 going here, which means 1 going from 0 to 1. So, only 1 here, 2 here, 4 here, 0 moves from that side. So, only this guy into this guy, that will survive. Here 0 into this, 0 into this, 0 into this, they do not mean nothing, anything, and here 2 into 0, 4 into 0 and so on means nothing. So, 2 into 1. So, you see this entire sequence is shifting gradually to the right, and overlap initially I had, this much XRGRs overlap, it was overlapping between these two and these two. Others were, either non-zero here to 0 here, or non-zero here, 0 here, or 0 in both places. So, these two places. Then it moved further to the right, 4 came under this, 2 came under this, 1 came under this. That time I had maximum overlap. Okay. If I align, 1 came under this, 2 came under this, 4. So, maximum, all 3 are overlapping. If I shift further, 4 goes out, only 1 and 2 they are overlapping with this. If I shift further, only 1 comes below this. So, overlapping only here, and otherwise no overlap. If I shift further, 1 will also go out. So, there will be no overlap. They will be multiplied by 0 from here, these will be multiplied by 0. That is, if we have 1 moving further, that is for next n. So, when before that, let me complete this. When for this case 1 into 2 only, that means here it is just 2, 0, 1, 2, 3. So, n equal to 3, for n equal to 3 also we found out value is 2, but if I go for n equal to 4, if I go for n equal to 4, then what will happen? This 1 will move here. Okay. What will happen is this, for n equal to 3, 1 came below this, right. So, 1 into 2, it will further move, it will be like this, 1 will move here, 2 here, 4 here, but this is outside, this will find 0, this will find 0. So, no overlap, this is meeting 0, this is meeting 0, this is meeting 0, this is meeting 0, this is meeting, so no overlap. Okay. So, I will get 0 value. If it shifts further to the right, continues to do that, there will be no overlap, so it will remain 0. So, I will have 0 values, which means after this we will have zeros, 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 zeros. So, that is for the positive side of n. For the negative side of n, minus 1, minus 2, minus 3, if it is minus 1, it will be gr plus 1. So, gr is to be shifted back by 1. Then I have to see the overlap and multiply. This you can carry out. If gr is shifted back, this 0 will come here, 4 will be here, 2 will go, 1 will go. So, 0 comes here, 0, 4 comes here, 2 comes here, 1 comes here, okay, and 0, 0, all these zeros. So, only these two overlaps. okay, 4 into 2, this with 0, this with 0, this with 0, this with 0, so on. 4 into 2 is 8, which means output will be 8 at minus 1. Okay. If I go further back, n equal to minus 2, it will be G R plus 2. So, G R will be shifted back by 2, that is, this will be shifted by 1, it is already shifted by 1 to the left, 1 more. So, 4 will come here, 4 will come here at minus 2th point. Here this 0 will come, this 0 will move here, another 0 here, like that. 4, 2, 1, dot, 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 dot. Now, you see there is no overlap between H and this. This meets 0, 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 this meets 0. So, output is 0, and as n becomes more and more negative, output continues to be 0, which means 0, 0, 0, 0, like this. This is the output. All right. Suppose I have an x n, if you convolve with delta n, what is the result? So, you write again x r x r any sequence dot 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 dot. In fact, this you can do directly from here, say x r delta n minus r, right, r equal to minus infinity infinity. Now, this delta, this is 1 only if the argument is 0. Argument 0 is r equal to n, r equal to n, it becomes x n. Okay. And if r is not n, for any other index, non-zero index here, delta value is 0, so output is 0. So, that means only term that survives is x n into 1, that is x n. So, if you convolve, then output at any index is same as x n. So, you get back your original sample. Okay. So, you do not need to do graphically. So, convolution by this delta n is always same as I mean, if you say take a sequence, convolve with delta n, you get back the sequence, because at any index n, if you are convolving, you get back the same sample x n. As I told you, n minus r, only when it is 0, this delta value will be 1. When it is 0, r equal to n, r equal to n means x n into 1, x n. For any other r in this range, it will be 0, so do not count. So, x n will come out of this summation. So, convolution between x n sequence and delta sequence, if you evaluate the convolution at any nth index, you get back your x n. So, all samples remain as it is. So, sequence comes back as it is. Okay. So, convolution by delta n does not change anything. If you convolve by say delta n minus suppose 1 or say delta n minus r, then what happens? N minus r, say the n minus m. So, you write x r delta n minus m minus r, okay, r equal to minus infinity to infinity. Here this argument r should be such that this argument is 0, then only this delta is 1. Okay. So, that x goes out, that into 1. For any other r, delta will be 0. So, r equal to n minus m, when r takes that value in this, when moving in this range from minus infinity to infinity, when it takes this value, then you have got x r minus n minus m, that goes out, that into 1, okay, that into 1, all other values are 0. So, if you convolve x n with some delayed delta, delta n minus m, convolution output at nth index will not be original x n, it will be shifted version, delayed version by m, which means every sample is shifted by m. So, sequence is shifted by m. M is positive, if m is positive, shifted to the right, m is negative, shifted to the left. So, convolution with delta n minus m means basically shifting the sequence. Okay. Now, before I conclude this section today, one interesting property I want to show, that suppose there is a linear shift invariant system, its impulse response is h n, you give a sequence x n of the form some number a, real or complex, to be general it is complex, a to the power n, not causal, n positive, n negative, for both we get values. What is the output? Output will be convolution, and I prefer h convolved with x, that form. X n is a to the power n. So, x n minus r is a to the power n minus r. Now, the beauty is this is coming in the power. So, a to the power n minus r you can separate out, is a to the power n into a to the power minus r, and a to the power n can go out as common because that does not depend on r. So, it will be into a to the power n out as common. What is it? The summation part over r. Now, you see this summation does not depend on index n, it is a global, it is a constant. You are just running this summation, you know value of a, you know value of h, carry out this summation offline, say a constant independent of n. So, for any index you want to find out y n, you have a to the power n by this common constant, which means a to the power n such a sequence that if it is inputted to this linear shift invariant system, output is same a to the power n, just multiplied by a common constant for any n. For every index n, if it is a to the power n, it is the same a to the power n. Only thing is, it has got a common amplitude factor constant for any n. Okay. This sequence is called eigen sequence. Because if you input, you can give it a name lambda as a function of a. A is your choice. So, lambda as a function of a times a to the power n. This is a constant. This is not a function of n. So, this is true for any n. So, this if you input a to the power n, you get the same a to the power n. All samples get multiplied by a constant factor, amplified or attenuated by constant factor. It is called an eigen sequence. This is a very important thing, and it comes from this concept of eigenvalue, eigenvector of matrices. Okay. Suppose I give you a matrix A. All right, square matrix. Now, if you multiply A with any vector x, you know how to do this, you will get another y. But y and x is it's not in general that y is just x, all sample multiplied by a constant, is not. Some x, some y. But for these matrices, there exists a class of vectors called eigenvectors x, where x must not be 0, of course, by definition. Underline means vector, underline means matrix, uppercase letter underline matrix, lowercase letter underline vector. There is exists a class of such vectors, non-zero vectors, so that for them if you do a x, you get back same x, all samples multiplied by a constant lambda. Then that x is called an eigenvector of A, and this lambda is called an eigenvalue of corresponding eigenvalue. It means, suppose I am in a 3-dimensional world. So, x is 3 coordinate, 3 things, x1, x2, x3, this is your x. you can view as though in a 3-dimensional world, this is x coordinate, this is y coordinate, z coordinate. So, it is pointing to a vector, pointing to a vector. In general, A into x will be another vector of 3 elements. So, that will be another direction. But if it is an eigenvector, then all elements multiplying by lambda will be the output, means vector direction remains same, every value, coordinate value just gets expanded or contracted by a constant factor lambda. So, direction does not change, A times x keeps you in the same direction, only value of magnitude or length of the resulting vector is different, maybe it is lambda times the original one. Okay, the length changes, but direction does not changes. Then x is an eigenvector, lambda is an eigenvalue. Okay. Why this is important is because suppose I give you one eigenvector x1 and it is having eigenvalue lambda 1 eigenvector. So, this satisfied. Another one, suppose this you know, what is lambda 1 you know, what is x1 you know. Another x2, there is also another eigenvector lambda 2 times x2. Then if I give you neither x1 nor x2, but a linear combination, you can carry out this product from this knowledge, because A into C1 x1, C1 is a scalar, so C1 can go out, A x1, you know A x1 is lambda 1 x1, directly put from there, and A into C2 x2, C2 can go out, A x2 which is lambda 2 x2. So, just C1 times this, C2 times this, you do not have to recompute this if you know them. Okay. That is the big advantage. Now, the question is, if I give you any arbitrary vector x, if you could write it as a summation of eigenvalues, eigenvectors, if you could write it as a summation of C I x I equal to maybe 1 to how many p. So, p eigen, there can be maximum p eigenvectors. Then A into x is very easy to compute. A times this, C I go out, A x I is lambda I x I. So, C I lambda I x I. Okay. You do not have to carry out this product, you just have to add them. This is a big advantage. Same thing here, but I should be able to write x, any x in this form. That depends on the eigenvectors. In some cases you can, some cases you cannot. Okay. A to the power n gave you lambda a to the power n. All right. So, suppose I have it 1 a1 to the power n, this is also of this form. So, it will be of the similar forms, it will be an eigen function, eigen sequence of this, output will be same lambda, but lambda a1 because it is not a, it is a1 times a1 to the power n. Suppose I have given you a2 to the power n is lambda a2 to the power n, it is known. Okay. Then if I give you a new sequence C1 a1 to the power n plus C2 a2 to the power n, what is the output? If I want to find out, that is, if I want to convolve H with this, I really do not have to carry out convolution. I know that my operator, this is a linear system. So, capital T, if it is the operator T, T working on this will be response due to this and response due to this, because it is a linear system, and response due to this means C1 can go out, T working on a1 to the power n, and C2 can go out, T working on a to the power n, and the two responses will be added. Okay. Two responses will be added, and this I know what this response is, because this is an eigen function. So, I can directly put, I do not have to calculate C1 lambda a1 C2 lambda a2 to the power n. Okay. This is a big advantage. Given this kind of sequence, which is a linear combination of eigen sequences, their output can be calculated directly from them only. I do not have to calculate a convolution involving so many terms, and multiplying, adding and all those things, very simple. Question is, if I give an arbitrary sequence x n, if I give an arbitrary sequence x n, not necessarily in this form, a combination of, can I still write it as a superimposition, that is summation of these eigen sequences? If so, then convolution of that x n with h n becomes damn easy. We will show in the next class that if you take a to the power a as say e to the power j omega, that is a complex number with magnitude 1, then it is possible to get, I mean, for any arbitrary x n, and you know it is where if this, that is in, you are giving e to the power j omega n as the input, you are getting t working on e to the power j omega n as output, which will be some lambda, maybe a function of omega into e to the power j omega n, because it is an eigen function, it is of the form a to the power n, a is e to the power j omega, so a to the power n comes back lambda omega. Then this is given, then for any arbitrary x n also, I can write it, I can express an arbitrary x n in terms of this e to the power j omega n kind of eigen sequences as a linear combination of them for various values of omega. And so therefore, output can be calculated easily without carrying out convolution sum. More of that later in the next class. Thank you very much.